And here's the next video, talking about the cosmic microwave background, trying to get at what the more precise temperature or redshift at which the universe goes from being opaque to being transparent. We have just computed the interaction rate of photons with the background ions as a function of redshift. It depends on, the parameters that control how many charged particles there are out there. Depends on the Thomson cross-section and the speed of light, and also depends on the fractional ionization. And naturally, it has this sort of scaling, like 1 plus z to the power of 3, and that shows up because the number density of charged particles scales inversely as the cube of the scale factor, and so that scales like the cube of 1 plus z. Okay, what we want to do is compare this to the Hubble rate. We want to compare this interaction rate to the Hubble rate, and that is what will allow us to compare or to figure out when the universe goes from opaque to transparent. So we're going to compare the photon scattering rate to the Hubble rate, and we can write them both as a function of z. This may seem like this is a new thing that we're doing, but I want to just quickly convince you that this is like something that we've already done. This is the same thing as comparing, or yeah, it really is the same thing like comparing, if instead of comparing the rate capital gamma to Hubble, what if we instead compared their inverse rates? And instead of comparing their inverse rates, we actually multiplied both by a factor of c. So that would be a different kind of thing you could do, but is more or less comparing the same numbers. If you recall, what went in to the calculation of gamma, remember that gamma was given by number density of electrons, Thomson cross-section times c. So what that means is that what I'm really doing here is comparing 1 over the number density of electrons and Thomson cross-section to c times H inverse. So this is really the same thing as comparing the so-called free streaming length of photons to the Hubble distance. Okay, it will really be, it'll give us the relevant quantity. Like if the free streaming length of the photon becomes bigger than the observable universe size, then we say the universe has become transparent. But we'll follow along with Ryden and do this. We have our expression for gamma. And now let's just compute the Hubble constant. We've honed in on the redshift at which decoupling happens. That happens to be around 13 or 1400 redshift, and that is in the matter-dominated phase of the universe. So I can't recall if we had done this as a class, but I think at some point we computed the scale factor and also the redshift at which the universe goes from radiation-dominated to matter-dominated. That occurs at a redshift of around 3000. This is at a much lower redshift. In other words, the universe was bigger, more dilute, and that means that we're well into the matter-dominated phase. That is nice because it allows us to more simply compute what the Hubble parameter is as a function of redshift. During the matter-dominated phase, we're only going to consider matter, of course. That means that the Friedmann equation, is given by the Hubble parameter today, and then multiplied by the dimensionless density parameter in matter. And then what we could do is divide this by a cubed, but remember that's the same thing as multiplying by 1 plus z to the power of 3. So during this time, around the time when the cosmic microwave background was formed, then that should be the form of the Hubble parameter. Okay, well clearly what that means is that h is given by h naught times the square root of the density parameter in matter times 1 plus z to the power of 3 halves. You can look up the quantity, you can look up what the Hubble parameter is in units of inverse years or inverse seconds. You can look this up according to the benchmark model that's given in Ryden somewhere, probably a couple places in Ryden's book. You can then compute this, and this works out to be approximately 1.23 times 10 to the minus 18 inverse seconds. And then this does continue to scale like 1 plus z to the 3 halves. Okay? And then the last thing to do then is to compare when when is it true? When does the transition happen when the interaction rate of photons goes from being higher than the Hubble rate to lower than the Hubble rate? In other words, when does that transition happen? It happens when those two things are equal. Okay, this is a better sense of, if you like, when, what's the word I want to use here? We can call this last scattering of photons. Okay, what that means is you'd compare, well, the number that we showed up top, gamma involves the redshift. Should I bother writing these things down? Sure, why not? 5.0 times 10 to the minus 21 seconds times the fractional ionization as a function of z, 1 plus z cubed, that is equal to 1.23 times 10 to the minus 18 inverse seconds times 1 plus z to the 3 halves. You can then attempt to solve this for 1 plus z. Ryden does this. I think I'm not going to fill in the gaps, but you'll have to take a root, a 2/3 root. And what you'd find is that 1 plus z, for this equality to hold, you'd have to have 1 plus z is approximately equal to 39.3 divided by the fractional ionization raised to the power of 2/3. Now, x of z really, has to be done numerically to get this at every point, at every redshift. Let me just point out, though, this is actually from an older version of Ryden, but nevertheless has most of what we need. Yeah, this is an older version of Ryden. You'll notice redshift goes from left to right, increasing. In the newer version, it goes the other way. It doesn't really matter. But you can imagine using, trying to solve that transcendental equation and sort of honing in on a redshift that satisfies that equation. So you would pick this as the fractional ionization. You find the redshift at which this equation can be satisfied. And numerically, you'll find satisfied at z of approximately equal to 1100. I guess it turns out to be slightly bigger. You'll notice that's even lower than what we found before. In other words, the redshift at which the universe is half ionized, half neutral. It turns out that we expect photons to continue to be able to scatter with things, even when the universe is much less than half ionized. At that later time, the universe is even bigger, the redshift is even smaller, and so it seems that the time at which the last scattering of photons, so I'll put this as last photon scatter, seems to be much closer to 1100. Okay, finally I'll just make some comments. We've gotten pretty damn close without having to do the heavy numerics and heavy, non-equilibrium statistical mechanics. We've gotten pretty far. So let's just make a couple of fixes that would be needed to do this, with the fully adult way. Fixes needed include, but may exceed what I'm listing here. There's more than just hydrogen out there, of course. There's what we have neglected to also include as, for example, helium. So you've got more than hydrogen. You've got, you've got deuterium, you've got helium-3, you've got helium-4, etc. But really, the big players we're going to see are hydrogen and helium-4, but we've certainly neglected helium-4 in this analysis. There is certainly more than just the ground state of hydrogen and the fully ionized state, right? There are actually an infinite number of excited states of hydrogen, so maybe I can just indicate that here. The excited states of hydrogen have been excluded thus far. And of course, you can have You can have transitions from the ground state to the first excited state, and then, it's easier to ionize hydrogen from the first excited state to being fully ionized. Anyway, lastly, I'll just point out that chemical equilibrium, which we have assumed in this whole analysis, that hydrogen atom plus a photon going into a proton plus an electron is equally likely that way and going backward. That certainly breaks down at some point. And so, in other words, you end up in a non-equilibrium situation. There may, in fact, be more fixes here that I'm unaware of, but at least those are the important ones. In any case, it turns out 1100 is pretty damn close. In any case, Z of the last scattering, I'll write it as LS, is approximately equal to, nowadays we seem to have honed in on approximately 1090. That's LS, again, is the last scattering redshift for photons. And just to give some sense of scale, if we're really rough here, so let's just get a rough sense of scale. We have a last scattering. In other words, when this cosmic microwave background was created, was approximately speaking at Z of approximately 10 to the 3. The scale factor, which it goes like 1 divided by 1 plus Z. Well, Z is a huge number, so this is approximately 1 over Z last scattering. That means the scale factor was about 10 to the minus 3. In other words, the universe was about 1,000 times smaller. And lastly, the temperature at last scattering. Well, remember that goes like the temperature today divided by the scale factor at the time. In other words, this is approximately T naught times 10 to the 3. And since T naught is something like, 2.7 or so, I guess we're being very, very rough here. So this is approximately 3 Kelvin. That means the temperature at last scattering is approximately 3,000 Kelvin. Okay, and that just gives us a sense of scale, and that's going to, by the way, help when we start studying Big Bang nucleosynthesis. We'll see how the temperatures are much, much higher than 3,000 Kelvin. Yeah, I guess the last thing to point out here is, and there's some discussion of this in your book, is that as it turns out, right, there isn't a specific instant at which the cosmic microwave background is formed. Really, some photons have their last scattering earlier than other photons, and so in fact there isn't a single thin surface for the surface of last scattering. It's more like a thicker surface, and that has to do with something called the optical depth, which we won't spend any time on. But anyway, just know that that last scattering surface actually has some thickness to it.